All right, so with that being said, I think everything is good. And today we will finish our attention model and we will start to talk about unsupervised learning. So the students who plan to work on the first project, as I explained in our first lecture, we will have 3 options for you guys to choose as your final project. The first one is related to the GAN, Generative Adversarial Network. And today we will start to talk about that. So if you plan to work on this project, I hope you guys could put more effort into this lecture. And after we finished about the whole lecture of GAN, we will release our first project. So if you are interested, so you can already start. And after we finish this lecture, I will in web course I will create Excel. So like you can put your name under the project you are interested in. So like you can start work on that project. And our project is group based. So each project will have about 2 or 3 people. So if you have any like preference, you say, okay, you want to work with someone. So you guys just put your name together, marked like we are a group. So if you don't have any preference, I will randomly assign you to someone else so you can work on something together. So I will assign people who's interested in the same project topic together. So if both of you are interested in your GAN, with very high probability, you will be working in the same group. All right. Do you have questions about that? Like I think that will be more clear after I release the concrete, project topic and the project description. Okay, so now let's finish our attention model first, and then we will move on to the GAN. All right, so this is what we learned from last time. So last time we talked about the self-attention model, and we gave the basic idea about how to do that. And finally, we come to this step. So this is kind of summarized. So the basic idea is in this figure, right? So the input, so this is the attention layer. So the input is you can think of the input as a vector set. It can be a sequence of vector. It can be a set of vector. So it's just multiple vectors as the input. For example, if we have a sequence vector as the input, like A1, A2, A3, A4 here. So we have 4 input, and then we will have 4 output, B1, B2, B3, B4. All right, so each input will have 1 output. If you use recurrent network to do that, like every output will you compute every output based on the current input and the previous input. But for attention model, every output depends on the current input and some other input, like it can happen anywhere. So maybe B1 will depend on A1 and A3. So which input will affect the output all depends on the attention score. We described in the previous lecture how to compute the attention score. The basic idea is to find out how relevant the current input and the other input is. If it's very relevant, then the attention score will be very high. If it's not very relevant, then the attention score is low, and the B1 probably will not depend on this non-relevant input. So the way we do that is here. So this. So you can just so this table, this figure just summarize everything. So you put every A as a matrix as I, and then first we will have 3 set of parameters: WQ, WK, and WV. These 3 set of parameter can help you to compute the query matrix, the key matrix, and the value matrix. After you have these 3 matrices, you can just do the inner product of the query and the key. So you get the attention score, which we represent as A prime. And finally, the output is the value of the input weighted by the score, the A prime. So this is the basic idea of the game. And last time is there some echo?
Oh, I have a quick question.
Yes.
How does it go from A to A prime?
A to A prime is just a normalization. So A is the attention score, then A prime is a way to normalize it. So let's go back to this slide. I think it's showing. Okay. A prime. Let me see, where is it? Yeah, it's here, right? So you get, sorry, it's called alpha, not A. So the attention score is called alpha. So you have the alpha, and then you just sum everything, and you use the softmax, right? So you just use the exponential function and sum everything, and then divided each alpha by the summation. So the idea is just to normalize it to make sure that every alpha is a positive number, and the summation of all the alpha equals to 1. So this is very similar to the, when we do the multi-class classification, the last layer is usually a softmax. So we hope the summation of all the alpha to be 1. So we just do a normalization. So alpha becomes to alpha prime. Okay. And the A is just the matrix of alpha. All right, so that is the attention part. So except for that, we have something else. So today we will just finish the other part. So last time, the attention model just to tell you how relevant the current input and other input is. So there is no position information in the whole attention model, but we know that the position is very important. For example, as I give in the beginning, I give an example like I saw a saw, right? So the first saw is a verb and the second saw is a noun, right? So they mean different things. So the position of the word is also important. So we hope we can utilize this information to help us to make a better prediction. But in the previous attention model, we only consider the relevance of the input tokens. We never, there's no positional information in our attention model. So like we hope we can encode this information. Like in the recurrent network, the sequence are input one by one. So the position information, the time information are automatically encoded there. But here, since every words are input, we input every word in the network at the same time. So for the network, there's no difference between where the words exist, like the order does not affect anything. So we hope we can encode some position information in the whole network. So the way we do that, like there are several ways to give a position information. One of the most popular method is a handcrafted method. So like what we I put here. So this is some method. Like for example, if the word exists in the first place, then we use a vector like this, the first column to represent it. The color represents the value, like the yellowish is around 1, and the blue, dark green, I don't know, this color represents the -1. So for example, this sometimes the whole length of the input vector, the positional vector for each time is about maybe 128 or 256. Like we need to specify a length. So we use maybe a 128 vector to represent a position of each word. So for example, for the first word is the first column here, the second word, the second column. And so this figure is just is generated by some sinusoid function, right? So it can be some combination. I remember this is some combination of sine function and cosine function. And then you add them together, have this positional encoder. And also, except for that, you can also like try to learn from data. You use another network to generate the positional information. So there are several ways. I just put it here. If you're interested, you can go to the paper to see like the detailed method. But to be honest, from my side, what I have also done some research in this direction, and I found that there are not too much difference between these different positional encoding method. So that's why like people always go to the most simple one, the sinusoid function. So this function does not need to learn. So the value of the position is just varies with the position it appears. So if, for example, here, if it exists in the first place, it will be the first. I think it's not the first column. It probably should be the first row. I don't remember which one is which. So probably it's the first row is the first position. Second row is the second position. So and the third row is the third position. So we can just use this method to encode the positional information. Okay, and that is everything about the attention model. So, and after the attention model is proposed, it has a very, very wide application. And if you have heard about that, the transformer and BERT, these are two dominant method in the NLP domain, and both of them are based on the attention model. So the transformer is the attention model, and you probably need to add some technology called residual connection, and it will become transformer. And for BERT, it will be just the transformer, and you add some technology called pre-training, and you get this BERT, right? So this architecture are some real tech architecture which are already used and already launched in the current system you have been using. Maybe the Google Transform you use every day are based on this technology, right? So, and the basic idea, the most fundamental thing of this technology are the attention model. So I think everyone should have a clear idea about how it works. And so this is how we use attention for the sequential model, maybe for the language model. But attention model currently can be used to any type of input modality. For example, we can use the self-attention for speech. So as I explained in the beginning, the speech is a very long vector sequence. And what we do is usually we have a window to truncate a section, and then we take that section as a long vector. So that vector is the input at time t equals to 1. And then we move the window, get another vector, move the window, like another, so we have this sliding window, so we can generate a input sequence. After this input sequence, so here you can think of the like A1 is the input sequence at time t equals to 1. A2 is a sequence at time t equals to 2. So we have this input sequence, and we can do some job based on this input sequence. A difference between the speech and the language is that usually the self-attention model, the attention exists in a range. So when you're trying to decide what is the phoneme, or what is the when you do POS tagging, you don't need to have the attention to the input which is far away from you. For language processing, for natural language processing, for the word, maybe the attention can the current decision may depend on some word which is far away from you. But for the speech, the attention does not span like with a very wide range. So in this case, when people use attention model to speech, usually we do a truncate model. So for example, here, if you want to make a decision for A3, like you want to generate B3, usually you just truncate it for the neighborhood of 3 vector, right? So you only consider A2 and A4, and you don't need to consider A1. This is just the example. Actually, it's a little bit longer than the 4 vector. It's maybe 20 or 100. So if it's very far away, you just cut the attention connection directly, because like the speech does not have a very long dependence range. And also similarly, we can apply the attention model to image. You can also consider image as a vector set. So for example, like one way we do that is we can cut the image into a subset. For example, like we can say, okay, so this is one piece. This is another piece. So the image can be cut into a lot of small pieces, and then each small piece can be represented as a vector. And then you can just apply the attention model directly on this kind of input. So this method about using attention model for image processing are called vision transformer, like a vision, I think VIT or something like that. So vision transformer. So vision transformer is used to image modality.
So VIT is used for still images, and then there's VIT for video.
Yes.
Which is kind of cool.
Yes. Yeah, that's true. Yeah. That's true. Yeah.
Yeah, VIT was like an image is worth 16 by 16 words or something.
Mm-hmm. So. Yeah.
So with this, it kind of looks like convolution in some way. Like obviously it's a learned.
Very nice,
thing,
right?
like
so I'm glad you asked the question. See, this is the next slide. Is I want you to think about the difference between convolutional neural network and the self-attention model. So it's very similar. So what is the difference between these two type of model? Right. So remember, in convolutional neural network, what we do is we usually have this reception field. If you remember, every time we have a kernel, and the kernel we apply it to a reception field like this. So and then you can think like, why we have this idea, because we think this, if we look at a section, we think this section are highly relevant to each other. Right? Because you remember when we talk about CNN, if you want to do a big detector, the big usually exist in a region. So that's why when we do that, we usually consider a reception field which is located together. All the pixels need to be together in that region. But for self-attention, we also trying to group some pixels together, but the pixel does not need to be close to each other necessarily. Right, so for example, this figure shows you the difference. For CNN, we have this reception field, like the thing I draw here. But for the attention model, the reception field are learned. Right, so we learn, okay, this pixel are highly relevant to this pixel. So when we make some decision, we need to consider these two pixels together. But for CNN, we don't do that. For CNN, we just, consider like every range. So we just consider, okay, this is a kernel. Like after that, we remove the reception field. But for attention model, we learn the reception field. For each reception field, all the pixels can locate it everywhere in the image. So that's a difference. So in summarize, you can think like the self-attention can only so you can think of the CNN as an attention model that attends in a reception field. So the reception field is the attention. You can think of the like this. How should I say? So you can think of the CNN's reception field as the attention model when the attention score are 1. Right, so you think, okay, all these pixels are highly relevant. So all the alpha, the attention score for this are 1. And all other alpha are 0. So the CNN's alpha is, instead of learning the alpha, it's already specified that by this receptional field. So you can think of the CNN as a simplified version of self-attention model. And the self-attention model is a CNN with a learnable reception field, right? So we just learn which part is relevant to each other. So you can think like self-attention is a complex version of CNN. I'm glad you asked the question about the difference between these two models. Actually, these two models, there is a paper even discuss about the difference. So in that paper, they think like the CNN is a subset of self-attention. And if you're interested, just go into this paper. This paper introduced about how to set some parameter of self-attention, so the self-attention will reduce to a CNN directly. So that is a connection. And in the first class, we talk about, okay, if the model is complex, it will be easier, it can be overfit to the training data. And if the model is complex, we usually need more data to train the network. If the network is simple, then we can use less data to train the network. So in this case, if you look at this figure, this shows the performance of self-attention model and CNN on an image processing data set. So the blue figure here, the blue line here represents the self-attention model, and the gray line represents the convolutional neural network. So you can see that when the number of training sample is small, when we only have 10 million training samples, right? So the CNN performs better than the self-attention because this is a simple model. But as we have more and more training samples, the self-attention model will like beat CNN because self-attention is more complex. So if we have more data, then the self-attention model will win. So this also this is also true, like as all other machine learning technology. When the model is simple, then it goes for less data, and the model is complex, then it is good for more data. So it also tell you that if you're trying to solve some problem and which model you should select, it all depends on what kind of data you have. If you have enough data, the data is very complex, then I would suggest you to go with self-attention. Right? But if you don't have too much data, if you want to solve some image classification, but the training data size is maybe like this size, about 10 million, you can just go CNN and it can already give you a very good result. So that's the difference. And we can also think about what's the difference between convolutional neural network and self-attention. Right, so for convolutional neural network, if you remember, if we have a sequence of input and we're trying to use a memory to help us to bring the information in the past. So if we input the current information and then we input it to a convolutional neural network, we have fully connected, we have output. And this hidden layer is kind of a way to save the memory of the past. And then we bring this information to the next time, combine the input of the next time and have the output. And we keep on doing that until we have the prediction for the final time. So this is the RNN. And for attention model, you can think we have a vector set. And then the output is based on this vector set. So if you compare this to different model, you will see the difference. All right, so one difference is that for the convolutional neural network, the vector are input in a sequence model, right? So if you want to make a decision at this at the end, you need to wait until all the input and then you can do this step by step. But for the self-attention model, you don't need to do that sequence. Everything is parallel. You don't need to give the results for the last token before the middle one, right? You can output everything at the same time and you can process everything at the same time. But for the recurrent neural network, you cannot do this in a parallel manner. You need to do this sequential. So what's a good thing for parallel? The good thing is you can use the GPU or TPU to help you to speed up the process. Right? So if you can reduce the processing time, if you can solve everything in a parallel manner, you can reduce the processing time. Then at the same time, you can use more data to train the network. So that's why self-attention in this sense, it's performs better than the recurrent network. All right, so one last thing, in this class, we haven't really talked about graph neural network, but actually I think because I think the time, we don't have enough time to cover the graph neural network, but the basic idea is very similar to the convolution neural network or the recurrent neural network. For graph neural network, there are some connection, like there are some node, and there's some edge connect to different nodes. And then when you update the vector representation of each node, you take the information from its neighborhood and then update it. So if we can, of course, apply this attention model to graph. So like I represent here, we can use attention matrix to represent how relevant each node is. For example, if there is a connection between node 1 and node 8, then we will have a large attention score for 1 to 8 and 8 to 1. And if we have a connection between 1 to 6, then we can have a large value between 1, 6, and 6, 1. So this is maybe a binary. So if you can represent as if there is a connection, you put the attention score as 1. If it's there's no connection, for example, like some other like 1 to 2, if there's no connection here, you can put a value 0 here. But this is just a binary. You can also put it as a continuous value to show how relevant these two edges. For example, in social network, if these two people are very close to each other, then the connection, the attention score should be large. And if the two people does not know each other, then the attention score should be a very low value. And also it depends on how many common friends they have. You can set the different value for the attention score. Right. So like you can apply this similar idea to the graph neural network and get this network called the graph attentional graph neural network. Then like what I said, the attention model actually can apply to all different kinds of input set. As long as the input is a set of vector, you can apply this technology. Okay, that is everything about the attention model. Do we have any questions before I end it?
Yeah, one quick question.
Yes,
so
sure.
The previous slide, you called it an attention matrix, but it looks very similar, if not identical, to an adjacency matrix.
Yes.
Is that just how we're analyzing the graph? Or am I missing something?
Right. So it's very similar to the adjacent, as I explained. Like for this one, yes, it is, because I said if it's a connection, you put 1 here. If there's no connection, you put 0. So in this case, it's exactly the same as adjacent. But in the attention model, one thing is that this value may be learned, right? In the adjacent matrix, usually we use the adjacent matrix to describe a figure, to describe a graph. So this value are usually given you before you're doing some work. But in this case, in our case, for this attention matrix, actually this value are learned. You don't know this in the beginning. These are all parameters you need to learn. So that's the first difference. And the second difference is for the adjacent matrix, it can only be 1 and 0. But here, for the attention matrix, it can be any value between 0 to 1. It can be 0.7, 0.6, right, to represent how relevant this is. So I think that is the two difference between the attention matrix and the adjacent matrix. Does it sound clear to you?
So I guess that makes it a bit clearer. I mean, I've heard of adjacency matrices that have non-integer values, but my question is, that kind of implies that the structure of the graph is learned then in that case.
Yeah.
Oh, so that's what it's implying. That's actually really cool.
Yeah.
You just have a set of nodes and then it learns how they're connected.
Right. So usually, like, the reason like we want to learn that is because there is not a very concrete description. Right. So we don't know like how relevant these two nodes is. So that's why we hope the network can learn this information, and then we use this information to help us to make some prediction at the end. So this whole thing, like we only give you some graph, and based on this graph, you make the final decision, and the intermediate step, how it's connect, how relevant each node with each other, are all learned by the data. So it's kind of a black box. You don't know how it works, but just based on this method, the network can learn this for you. So that's why like people like to use it recently. Okay. So now I will, close this topic and go into a brand new topic. All right, so this is more interesting because, this actually recently people think that in machine learning, convolution neural network, recurrent neural network, and graph neural network are the most popular deep learning technology, like maybe 3 or 5 years ago. So in 5 years ago, people keeps on talking about that 3 architecture. But recently, if you go to the, like, if you have any chance to do an internship at this technology company, you will see that currently the most 2 popular technology people keeps on talking about is, one, the attention model. Second is this generative adversary network. So actually this is one of the most popular topic. So that's why we should spend some time to explain how it works. So now we are entering a totally different domain. So in all the lecture before, we are talking about the supervised learning, and now we move on to the unsupervised learning. So for unsupervised learning, usually we can try to classify the topic into 3 types. So the first one is called clustering. Clustering means that we're trying to put something similar into a group. For example, if we have trees like this, and if we have different type of trees like this, if I don't give you any label, you will think, okay, this is one group, this is another group. You just group something similar to each other. So this is called clustering. And another problem is called dimension reduction. Dimension reduction is trying to use a low dimensional vector to represent a high dimensional input. Right, so we give you all kinds of different trees. You represent each of them with a low dimensional vector. So this thing is very useful. It's because this is a good way to learn a representation for the input data, right? And this representation can be used later to the supervised learning. So this is how we combine the unsupervised learning and supervised learning. So if you have the data like this, and if you have a good representation, and later on when you input the data to a neural network, you don't input the original image, you only input this learned representation, and it can highly simplify the whole learning process. And with a good representation, the final performance will be improved a lot. So later on, we will also introduce about how to do this thing, how to learn a good representation. And the third kind of problem is called generation. Generation means that you just input some random number or like some number from a simple distribution. And you, after you input that into the function, it will output a complex distribution. For example, like this tree. This tree are a very complex representation. So you input 1, you output a figure like this. You input 2, you output a figure like this. So this is called generation. And today we will focus on this generation. We will talk about the generation first. And if we have time, well, we will cover the other 2, right? Because this is something like related to our project. So I would like to go with this one first. If we have time after we finish the topic related to the 3 project, we will come back. All right, so the network which can do this job to generate the image based on some random number is called generator. Generator is like that. So like what all the network you learned before is like this. You have an input X and you have output Y, right? So the data appears like a pair, right? So you have a cat of image of cat, you output something called this is a cat. You input a sentence, then the output is like maybe if you want to do sentiment analysis, if you input a sentence, then the output will be either positive or negative. So they're always like, if you have a fixed input, you always have a fixed output. So the generator is a little bit different because we don't want the output to be fixed. We want it to be some random number. So in order to realize that, instead of input X, we also have another input called Z, which is sampled from a very simple distribution. And then we want to, based on this Z, we want to output some other vector, right? So every time I sample from Z, a simple distribution, I output a Y. Sample from another Z, output another Y. Another Z, I have another Y. So I keep on doing that, and then I can generate a very complex distribution. So if you look at that, one feature which is very, very important here is that the input distribution need to be simple and the output distribution is complex. So what is a simple distribution? Like one example is a Gaussian distribution. A uniform distribution is a simple distribution. As long as you can sample from that, it's good. So like which one is better? Is Gaussian better? Is a uniform distribution better? Is a Bernoulli distribution better? We don't know. So usually, to be honest, from my side, there are not too much difference between Gaussian and uniform. Bernoulli is a little bit different, but Gaussian and uniform distribution, no matter which one you use, the output will not be too much difference. The network will learn how to mapping from this simple distribution to the complex distribution. For now, you can just think about every time you use that, just use Gaussian, right? So, and then you have this output. So the next question is, why do we want that, right? So previously we have a fixed input and we have a fixed output. So that is good. So why do we want to output Y, which is random? Why do we want to have this random output? So here is an example of video prediction. Right, so this is a video of Pac-Man Go. So I guess you guys probably you have been playing with this game before. So this is Pac-Man and it's trying to like eat all these things. So this is a video game. And the task here is called video prediction. And what it does is based on this input previous frames, and it want to output what is the next frame. Right, so it will try to output Y. Y is the next frame. So if you think about this, if you use the fixed network, right? So if you input this previous frame, you want to output a fixed output frame. This is the result generate. Look at the left. So at some point, if you're looking at this, the Pac-Man will become separate into two figure, right? And sometimes it have some shadowing behind it. Right, so when Pac-Man is coming here, it's always separate into two things and go into different locations. But actually, this is not true. The reason it generates a figure like the Pac-Man can go into two directions is because sometimes, based on the training data, at this point, sometimes Pac-Man go left and sometimes Pac-Man go right. So with maybe 50% probability it go left, with 50% probability it go right. And after we combine that, it will generate a Pac-Man which go in both left and right. So this is not true, right? Because Pac-Man will not go both left and right. The reason we do that is because of the training data, and going left and going right have the similar probability. So that's why we have the figure which go two directions. So in order to solve this problem, we don't want the Pac-Man to go both left and right. So we just want to sample from that, right? So if we have a simple distribution, every time we just sample it. So in this case, Pac-Man can go either left or right. So this is a true result. This is something we want to use for this case, right? So if we sampling from a simple distribution, maybe sometime we will generate something like this. It will go left, and sometimes it will generate a figure like this. It will go right. Okay. And in this, so what kind of application we have for this technology? So one thing is called, sometimes there are some tasks which need creativity. For example, if we want to create some figure, some picture. So if we do, like say, if I describe something like character with red eyes, and I want the network to generate some different character, right? If I ask you to draw a picture of character with red eyes. If I ask 100 people to do that, probably I can generate 100 different figures. Another application is a chatbot. So if I ask the network, do you know who is in the Big Bang Theory? So the network can output all kinds of different characters, right? Penny, Sheldon, like all different things. So for this type of application, we need a network which can generate output. And this function is realized by a network called generative adversarial network. And now let's go into the detail about how it works. So first, I need to tell you, like as I explained, GAN is a very, very popular technology. And recently we have a lot of variation of GAN. So after GAN was proposed in 2020, I think it's 2014, right? Around 2014 in that year. And after that, we have all kinds of different GAN, like AC GAN, B, like B GAN, C GAN, D, all kinds of different name of GAN. So as long as there is an improvement of GAN, we just add some letter to represent this is the new version of GAN. And there in GitHub, there is a GitHub called the GAN zoo. So it tells you that how many GANs it have. I think for now, it should be at least 500 or almost, I think maybe we can reach 1,000 different type of GANs. So you see like how popular it is. And even like the same name. So some people, the SGAN can represent all different things. So the name are already replicated too many times. And sometimes, for example, because one thing is when people want to call a GAN, he proposed like AE GAN. But since all other, Latin prefix are already used, he just choose another prefix, and he needs to explain why he used this prefix, because like all other letters are used, so he has to use some Latin prefix. That's why, like, if you search online, like, make sure that when you look at the name of GAN, look at the content, because the names are all very similar. Now let's start with the first generation again. Let's talk about the basic idea again, and probably we will cover 3 more different variations, because that is all you need to use for your project. So first, let's talk about the unconditional generation. For unconditional generation, let's just remove this X. So think about the unconditional generation as if we have an input, like a random input, and then I will generate some random output. So the random input can be sampled from a simple distribution, for example, the normal distribution, for example, and probably it can be just like maybe the length will be a 10 element vector or 100 element vector. So it's just a small vector from the normal distribution. And then you can generate a high dimensional vector from this low dimensional vector, right? So for example, if you have a 10 dimensional input vector, you generate an anime face like that. If you sample another one, you generate another anime face, and keep on doing that, you can generate all different kind of anime face. So this is a task called, we will use this example, anime face generation, to explain the idea. So the generative adversarial network are composed by 2 parts. One is a generator. We're trying to generate this face. And the other component is called discriminator. So the discriminator is trying to do one job. It's trying to differentiate whether the image is a true image or a fake image. Right? So if you input image to the discriminator will output a scalar, and the larger value means that it is a real image, and the smaller value means it is a fake image. So the discriminator is just a function. You can use a type of neural network to represent that. It can be if this is image, of course, you can use the convolution neural network. You can use the transformer, like you can, or the attention model we just improved. You can use any type of, architecture, depends on the modality of the input or the type of the input. So this is a discriminator. So for example, if we have a image like that, this looks very real, then the output for the discriminator should be around 1. If it's like this, it should be 1. And if the image is something like this, it's not, is apparently this is something not real. So the discriminant value will be very small, will be like 0.1. And if it's something like that, the value will be 0.1. Right, so we use the discriminator to help us to differentiate whether this is a real image like this or this is just some fake image like this. So let's think the basic idea of GAN. We can use the example to show the basic idea of GAN. So for example, this is a figure of a kind of butterfly. So this is not a leaf. This is a kind of butterfly. And this butterfly is so it can, because of the evolutionary theory, it is evolutionated from a very original version like this. So in the first generation of this type of butterfly is like this. It's very colorful. It looks like a butterfly. But the problem is a kind of bird usually eat that. The bird eats this butterfly. And the way the bird can know the butterfly is it knows that this butterfly is very colorful, it's not brown. So in order to escape from the bird, the butterfly is evolved to this kind. So it's trying to become brown so it can fool the bird. So the bird cannot differentiate the butterfly and the leaf, so it can survive. But however, the butterfly can evolve, so the bird can also evolve. So after a while, the bird know, okay, these are also butterfly. This is different, the difference between butterfly and the leaves are butterfly do not have wings, but leaves has wings. So in this case, the bird can still differentiate what kind of object is butterfly. It can still find it and eat it. So in order to survive, the butterfly trying to evolve again to become like this. So this is a butterfly, but it looks like leaf. So it's trying to add some wings in it to fool the bird. But the bird can also evolve and learn how to differentiate from this type of butterfly and the real leaf. Right, so this is the basic idea. So we have a butterfly trying to evolve, trying to fool the bird, and the bird are also involved trying to differentiate a butterfly and other leaf. So, so this is a good metaphor for our generative adversarial network. So you can think of the butterfly as a generator. It's trying to become more and more real to fool the bird, and the bird can be seen as a discriminator to differentiate the butterfly and leaf. This is very similar to the idea of GAN. So let's see how the GAN works. So the GAN is like that. So if the GAN trying to generate some real image like this, the first generation of GAN, it will generate some image like that. And the first version of discriminator will think, okay, this is fake and this is real because this is not colorful. Right, the real image is colorful and the image you generate are not colorful. So in this way, the discriminator can easily differentiate these two types. So in order to generate more real, image, the generator will, the second generator, like second version, will generate something like that. So it will make the image very colorful to fool the discriminator. Okay, after that, the discriminator may not differentiate this image and this image. So it needs to improve, and maybe it understands that the eyes or the shape or some other features are not different. Like for example, this one has very vivid long hair, very big eyes. So it learns the difference between this type of image and this. So in that case, the generator need to be improved and then generate something like that. And the discriminator keeps on improving for several generations. So you can think of the generator and discriminator are kind of adversary to each other. Right? So the generator trying to fool the discriminator and the discriminator trying to judge generator. So that's why this is why we call it adversarial network. So let's try to summarize the algorithm in a more formal way. So think about that. We have two networks. The network can be any type, the convolution neural network, the recurrent neural network, the graph neural network, the attention model, like all different kind of network. You have two network. And first, you just randomize all the parameters of these two network. And then first, we fix the generator and update the discriminator, right? So we trying to, you see, like we trying to input some vector and to the generator, and we'll generate some image like that. So this is not the, I think this is not the picture of the generation of the generator. Usually when we first generate some image, it's not like that. It's just some like very random noise. You cannot even observe any type of information from that. You cannot see any figure like eyes or anime face like that. It's usually something looks very, very bad. It's just like some random noise. So then you're trying to train the discriminator. How to train that? You just get some data from your database, the real image, and then get some data generated from the generator, and then like have this two type of input, and then input that to your discriminator to train the discriminator. You input this type, so actually you just like do that as a classification problem. You generate some image from the generator and label that as 0, and you sample some image from your database and label that as 1, and input this two type of input to your discriminator and train the discriminator. Then the discriminator will assign 1 to some image like this, and will assign 0 to some image like that. So this you can think of this as a classification problem. You can also think of this as a regression, right? So for this kind of input, you give it this as a high score, and for this kind of input, you give it a low score, right? So in this way, the discriminator can learn a function to estimate the score for this two type of input. In step 2, after we fix this discriminator, we will update the generator, right? The goal of the generator is to fool the discriminator. The input of the generator is a vector, and the output is an image like that. And then after we input the image to the discriminator, we hope the output of the discriminator to be as large as possible, right? So in step 1, remember, when we input the image generated from the generator, we hope the output of discriminator to be as small as possible, right? But in the step 2, the output of the generator, we're trying to make this as large as possible. But this part is fixed. The discriminator is fixed, and we're trying to update the parameter in generator so that at the end of the discriminator, it will have the high value. It will increase that. In order to increase that, the generator may generate some image looks a little bit real than before. So you can think of this as a large network. So you have two networks. One is for example, maybe the generator, you have 5 layers, and discriminator have another 5 layers, and they combine to have into a large network. And in the middle part, maybe one hidden layer, the output of the hidden layer has the same size as the image in the data set. So we hope this the output of this hidden layer to be very similar to the image. And then after you have this architecture, what you do is you just train that iteratively. So first you fix the generator, you train the update, you update the discriminator, and then you fix the discriminator, you update the generator, and then you just do this iteratively. Right? After that, you just use this generator to fix that and update the discriminator, fix the discriminator, train the generator. So it just keeps on doing training the generator and discriminator alternatively. So finally, I want to show you guys how the result looks like. So this is a face generated. This is some real result some other people generate. So after 1000 updates, you will generate some image like that. And after 1000, the image, the generator learns how to generate figures with this eye, this big eye. So it will learn, okay, yeah, for an anime face, it need to be colorful and it need to have these big eyes. And after 2000 updates, it's the hair are more real, the face looks like more real. And after 5,000, it looks even better. After 10,000, this is a result after 20,000. So for the 20,000, it's already very good. Although, like for example, so here there's some figure, there's no mouth, and the face looks a little bit twisted. I don't know. It's not very good, but at least it's something which can be accepted. And after 5,000, it's even better. And in 2019, I just want to show you that although this is not generated by the very basic version of GAN, it's generated by something called StyleGAN. This is the result it generates. Right, so if I take the image and ask you to look at that, probably you cannot notice the difference between this image and the real image. And this is something really nice. And if you're interested, probably we can talk about this type of technology later. And the GAN, generative adversarial network, can not only generate the fake image, the anime face, it can also generate some real face. So this is some face. These are all the fake face generated by the GAN. So you probably will ask why do we need that, right? So this is a very interesting application. Is like this is called something called face combination. Right? So for example, if you have a face of man like this, looks very serious, and the face of woman looks like a very happy face. And if we want to combine this face together, right? So like if you do some intermediate, interpolate it with some intermediate value, then probably you will generate, the man will become like less serious and become happy, and then looks like a woman. And you want to generate maybe like two person together, like how do we transfer one person to another? Probably you can do this. And also, like if you have a people's face looking left and another people's face looking right, and if you scan, probably you can generate a face looking in the middle, right? So that's a very amazing result for the GAN, because it's not a result in generate a figure with two face looking left and right. It generates one face looking forward. So actually, this is you can think of this as kind of intelligent. It's not just a brute forcefully combined two face. It's really generates some face which looks real, right? So this is some application of GAN. And you know, like the GAN is involved with a very long generation. The first generation GAN, you know, GAN was by the way, the GAN was proposed by someone called Ian Goodfellow. He is working at Google when he proposed this architecture, and then he went to Apple. I think recently he moved back to Google again. I don't know. Like when I was at Apple, he's also at Apple, so he's a kind of a very popular person there. And actually, the first generation of GAN, the first GAN he proposed can only generate something like that. It's not very good. Probably you cannot even tell what is really like in the image. But after some generation, as I said, it can generate something like this. It's still not very good, you know, like again, maybe something like that, right? So it can generate something which is, you know, not something intuitively true in your mind. It's like this. It's like this tennis, like what do you call it? Tennis ball dog. Maybe it can generate some funny figure like that, but the result for the other one are already very good now. And there are some things called, although GAN is good, but a problem for GAN is that GAN is very hard to train. So if you learn from, you know, from other people, if you're working on this project, you will think, okay, the GAN is so amazing, it can generate something really nice. But when you do that, the figure you generate probably is not very good. It's probably very, very bad. So there is a thing called no pain, no gain, right? No pain, no gain. So like if you do that, you will understand how painful the whole process to train a GAN, which can really works. So but I think that is a very good exercise, and I hope someone when you do the project and when you present your result at the end of the semester, I want you to show how painful it is. I want you to show what is the first GAN, what's the first result you generate, and how you improve that, how you solve the problem, and how you get the GAN which can really works at the end. The reason for that the GAN does not work very well is because, you know, one simple question is, we know that the generator and discriminator can help each other. But the problem is, think about it. If the generator cannot be trained at first, if the generator cannot tell the difference, then if the discriminator cannot tell the difference, then the generator is failed to improve. If the generator failed to improve, and then it cannot fall the discriminator, and the discriminator will fall to improve. Right? So if one thing cannot be trained, the other it depends on it. So the other network cannot train either. So that's a problem for how to at least get one of them to be trained at first. There are some tips online. So if the GAN does not work, there are some technology we can use to try to make it work. So I list all the technology here. So when you work on your project, I guess you probably need to come back to this slides and take some technology from here to help you to really make your GAN work. All right, so that is a basic version of GAN. And I think today we probably will just stop here. And then in our next lecture, we will talk about the conditional GAN. All right, so let's just stop here because this is already a full topic, and next time we can start from something new. Before I stop, do we have any questions?
Yes, so I've heard of one issue training GANs is called mode collapse, and that sounds awfully similar to the issue you described on slide 30. Is that what that is?
Yes, that's true. Right. Actually, I mean, are you talking about this slide? This one? This slide?
Yes, that slide.
Actually, no. That is a different issue. This is one issue, and the other is a different issue. So we will talk about the mode collapse thing. So the mode collapse means that probably I probably can find some figure. Yeah, later on you will see that. The mode collapse means that when you generate some figure, then the figure will more or less become the same. Right, so you will keep on generating the similar figure again and again. So because after you find something really works, the network likes to keep on generating that type of image, right? This is good because you find something good, but the problem is you don't have the you don't have the diversity. You want it to be like all kind of different anime face, for example, and looks different. But for that one, you will always keep on generating the similar thing, right? So that is not good. So we will talk about that later, like when we go into that topic. We will be there. Okay.
Okay, so basically it's a loss of creativity, but not necessarily a loss in
The reason for that, you can think about that. The goal for generator is trying to fool the discriminator, right? As long as it can generate something which can fool the discriminator, the job is finished. It's reached its goal. It doesn't care about the image is generated variance or is it similar. Right, so that's a problem. Actually, let me see if I have a figure here. I think in the later, maybe not in this slide. In the previous slides, I actually have a figure. Yeah, this one. All right, so we will talk about that later. If you look at this, after several generations, the figure, you see, like the real data is like that. Later on, it will keep on generating something similar. So if you look at this one, this figure, probably you will see a lot of face looking, I mean, let me see if you looking like maybe this one, like it's always like to generate some similar figure, right? So this one, right? So this one, all the figure are liking this, right? Because this figure is good. It's a very good generation. So as long as it generates something which can fool the discriminator, it will keep on generating this face, right? So this is called the mode collapse. And then there are some technology to solve that problem. we will talk about that later.
Cool.
Okay, okay, that's good. So I hope you guys enjoyed today's lecture, and I will see you guys on next Monday. And in the Monday's class, probably we will have another quiz. So make sure you can attend the class. All right. Okay, then I will stop here and see you next time.